Welcome to this video on solution strategy for solving frame problems after you have drawn all the free body diagrams. I would recommend that you should watch these three videos before watching this one. Before we get to the frame problems, let me draw your attention to this textbook where you will find a lot of solved examples, and also to this software from Actus Potentia. This software will help you solve engineering statics problems. Let's look at our example 1. So here we have a frame, and here we have a multi-force member and a two-force member. First, let's draw a free body diagram for the entire structure. At this pin, since it's connected to a multi-force member, we add two reaction internal forces, AX and AY. This pin is attached to a two-force member, hence the reaction force from the pin is along the member. When a pin is attached to a two-force member and you put two components here, then you are making the problem too difficult for yourself. That is why it's important to recognize two-force members in frames, and for two-force members the force is along the member. So this is the free body diagram of the whole body, and in this free body diagram we have three unknown forces, AX, AY, and F. If we set the net moment at A equals 0, we can find F, and then horizontal force balance gives you AX, and vertical force balance gives you AY. Just because we have three unknown forces in this whole body, all three forces can be calculated by imposing the three equilibrium conditions: one moment balance and two force balance. So now, before we move to the next step, remember that AX, AY, and F are known. Now we are going to draw the free body diagram for the components. This structure has one complex pin, so we are going to draw a free body diagram for the complex pin, free body diagram for the horizontal member, and free body diagram for the two force members. So altogether we will have three free body diagrams. Here's the pin, here's the horizontal member, two force member. Let's add the internal forces. AX, AY, remember these two are already known. F is known. This is the other force acting on the two force member along the member, and this force has a action reaction pair at the pin. This is a multi-force member, so at the pin we will have to add two components, BX and BY, and we add the action reaction pair at the pin. Now, net horizontal force equals 0 at pin 1. Just because F is known, we can calculate BX. Net vertical force equals 0 at pin Y gives BY, so we can calculate BY. So now AX and AY and this F we calculated from the whole free body, and BX and BY, the two other unknown forces, we calculate that from equilibrium of pin 1 We didn't have to write the equilibrium equations for body 1. 3 whole body equations are used, therefore 3 equations for body 1 are automatically satisfied. Next example. So here we have another frame. We have 1, 2, 3 two force members. Let's draw the free body diagram for the whole body. AXAY. Just because this is a two force member, the force from the pin is along the two force member. Balance the moment at A gives F2, and the net horizontal force balance and net vertical force balance give you AX and AY. So AX and AY and F2 are known. In this frame, we have a multi-force member, 3 two-force members, and 2 complex pins. So we will have 1, 2, 3, 4 free body diagrams for the 4 members, and 2 more free body diagrams for the 2 complex pins. Let's add the internal forces, AX and AY, at this pin, which we already know. F2, we already know from the whole free body diagram. The two force member is in equilibrium, so at this end we have an F2. That F2 has a action-reaction pair force at the bottom pin. The vertical two force member, F1 and F1, this F1 has a action-reaction pair force at the top middle pin. The inclined two force member has 2 forces, F3 and F3. Then by Newton's third law, we add an F3 at the bottom pin and add another F3 at the top right pin. At this point, just because it's a multi-force member at this pin, we have to add Bx and By, and we add action-reaction pair force Bx and By at the top middle pin. Multi-force member, add 2 forces, Cx and Cy, and then add them at the pin Cx and Cy. So body 1 has 1, 2, 3, 4 unknowns. Pin 1 has 1, 2, 3 unknowns. Pin 2 has 1, 2, 3 unknowns. Pin 3 has 3 forces. However, we have already calculated F2 from the whole free body diagram. So we attack pin 3 first. F2 is known. We can write 2 force balance equations and can calculate F1 and F3. So remember, F1 and F3 are now known. With F1 known, when we go to pin 1, F1 is now known, so we can calculate Bx and By from 2 force balance equations. Then we go to pin 2, just because F3 we have calculated from here. Pin 2 has only Cx and Cy as unknowns, so we solve pin 2 to find Cx and Cy. Notice that now we have all unknowns determined and we didn't even have to write any equilibrium equation for body 1. So 3 whole body equations are used, therefore 3 equations for body 1 are automatically satisfied. Again, begin with the whole free body diagram, add forces, this is a roller, so there is no horizontal force here, only a vertical force, Ay. So in this whole free body diagram, we have only 3 unknowns and we can determine all of them. So Ax, Ay, Ex and Ey are now known. So now we will get to the free body diagram of the components. We have a L-shaped multi-force member, a two-force member, and a vertical multi-force member, and 2 complex pins. These are the components. Let's add forces. Force from the roller, Ay, already known. This is a multi-force member, so at this pin we have to add Bx and By, and Newton's third law, action-reaction pair, goes to pin 2. Multi-force member, add Cx, Cy, and Cx, Cy goes to pin 1, action-reaction. Again, the vertical multi-force member, dx, dy, and dx and dy goes to the top right pin. Then the two-force member, F, goes to pin 2, and this F goes to body 2. Then forces from the pin at the bottom, Ex and Ey, but remember, Ex and Ey are already known. So net moment, we start with body 2. Net moment at body 2 gives you net moment at body 2 at point D. Ex and Ey are known, so we can calculate F. And then by force balance equation, we can calculate dx and dy. So in this free body diagram, we had 1, 2, 3 unknowns. We wrote 3 equations and calculated all of them. After that, with dx and dy known, we can calculate Cx and Cy because there are only 2 unknowns, and also with F known, we can calculate Bx and By from here because F is known. So now dx dy comes out of here, Cx Cy comes out of here, Bx By comes out of here, and the frame is completely solved. We didn't have to write any equation for body 1 because we used the 3 equilibrium equations for the whole body. Next frame, 1, 2, 3 two-force members and 2 multi-force members, 1 complex pin. EXEY, force from the bottom right pin. BY, force from the roller. This whole free body diagram has 3 unknowns. We can completely solve it. And so BY, EX, and EY are calculated. Now we are going to draw the free body diagrams, all the members. and there are one complex pin because three members and the wall meet at that point. So this is one complex pin. This is a complex pin because there is a load applied, and this is another complex pin because three members meet at that point. Let's add the forces. Multi-force member, AXAY, Newton's third law, AXAY goes to pin 1. The inclined two-force member, F2 and F2, establishes the equilibrium for this two-force member. Newton's third law here and Newton's third law here. Two-force member, F3 and F3, keep this two-force member in equilibrium. We transfer it here by Newton's third law, and we transfer it here by using Newton's third law. The lower horizontal body is a multi-force member. So at this pin, we will have to add Cx and Cy, and then transfer Cx and Cy to the pin by using Newton's third law. That the force from the roller, which is already known from the whole free body diagram, body 2 is a multi-force member, so we will have two forces, dx and dy, and transfer those using Newton's third law to the bottom right pin, which is at this support. The vertical two-force member, F1, F1, keep this body in equilibrium. We have to transfer it using Newton's third law to this pin, and this member. So transferred here to the member at the top and transferred here to the pin at the bottom. So the only thing that's remaining is at this pin, we also have the wall, and so we add Ex and Ey. But recall that Ex, Ey, and By are already calculated from the whole free body diagram. Okay, let's check this out. At this pin, we have 1, 2, 3, 4 unknowns. This pin has 1, 2, 3 unknowns. This pin has 4 unknowns. We can write 2 equations. Nothing can be solved here. 3 unknowns, can write 2 equations. Nothing can be solved here. 2 equations, 4 unknowns, nothing can be solved here. So we are still searching. Body 2, 4 unknowns, we can write only 3 equations. We cannot solve this. But here, body 1 has 3 unknown forces, Ax, Ay, and F1. And we can write 3 equations and calculate Ax, Ay, and F1. As soon as we calculate Ax and Ay, so now Ax and Ay are known. So this pin 1 now has only 2 unknowns, and we can solve for F3 and F2. And after we calculate F3 and F2, F1 is calculated from body 1, so F1 is known. F2 is calculated from pin 1, so F2 is known, so we can calculate dx and dy. F3 is calculated from pin 1, so now this pin has only 2 unknowns, Cx and Cy. And now all the internal forces are calculated. We didn't have to write a free body, didn't have to write the equilibrium equations for body 2, they are automatically satisfied because we use the three whole body equations. A two-force member here, a two-force member here, a two-force member here, and a multi-force member here, load applied here and here. Let's put the support forces. AXAY, top pin, BXBY, bottom pin. So in the whole free body, we have four unknowns, but we can write only three equations. So no useful information is coming out of this whole free body diagram. Let's write the free body diagram. So the whole free body diagram, whole free body has three equations and four unknowns. Whole body equations are not useful. Move on to the free body diagram of the components. So we have four members and one complex pin here because it's loaded, one complex pin here because it's loaded, and one complex pin here because we have three interactions here, 1, 2, and the wall. Let's add the forces. Top pin, support force. Bottom pin, support forces. Two-force member. Another two-force member. Another two-force member. At this pin, just because we have a multi-force member, we will have two components, X and Y. So now all the free body diagrams are drawn. Remember, whole free body diagram didn't give us AX, AY, or BX, BY. So body 1 has 1, 2, 3, 4, 5 unknowns. Pin 1 has 1, 2, 3, 4 unknowns. This pin has only 2 unknowns. So we go to pin 3 and find F3 and F2. Once F2 is known, we can go to this pin and calculate CX and CY. When CX and CY are known, body 1 now has only 3 unknowns, AX, AY, and F1. We can calculate those. And then we can go to pin 1 because F3 we calculated from pin 3, F1 we calculated from body 1, so now we can calculate BX and BY. This is the whole body, top pin. These two forces, dx and dy, are coming from the channel in which the piston is moving, and there is some object here which is applying a force on the piston. So those are dx and dy. And then the right pin has bx and by. So this whole free body diagram has 6 unknowns. We can write only 3 equations. So whole body equations are not useful. We have to draw the free body diagram of the members. Top pin. At this pin, we have a 2-force member attached. So that is the 2-force member. At the other end of the 2-force member, we have a pin, which is this pin. And so we transfer this F1 to that pin using Newton's third law. Again, the second two-force member, application of Newton's third law, application of Newton's third law. The next complex pin, this is a multi-force member, so we add a CXCY and transfer it to the pin CXCY. We are now talking about this pin. The right pin, BXBY, and as before, the channel and the resistance from this green object here gives us dx dy. This free body diagram has only three unknowns, and we can write three equations. So that is a good starting point. Body 1, three equilibrium equations will give us Ax, Ay, and F1. So now with Ax, Ay, and F1 known, we go to body 2, which has three unknowns, F2, By, and Bx. We can write three equations and calculate the three forces. With F1 known from body 1, F2 known from body 2, we can go to this pin. With F1 and F2 known, we can calculate Cy and Cx. And with Cy and Cx known, we can calculate dx and dy. Now we are drawing the free body diagram for this pin. The cable and pulley detail are invisible in the whole free body diagram. So we have a pin here and a roller here. Roller, pin. This free body diagram has only three unknowns. We can completely solve it and find Ax, Ay, and dy. Let's go to the free body diagram of the components. This pin is a complex pin because we have a cable, a member, and the wall. So we have to draw a free body diagram for that. This L-shaped member is two force, so the two forces will be aligned along this line. The support force coming from the wall at the left pin. Bx and By are the forces at the pin coming from the multi-force member. So we applied Newton's third law here. The two-force member, at this pin, the vertical member and the horizontal member are connected. This is the action-reaction pair at that pin. And then we will have to add the force from the roller. So let's review what is known and what is not known. Here we have Ax and Ay already calculated from the whole free body diagram. So the net force at the pin gives Bx and By. Ax and Ay came out of the whole free body diagram. We know Bx and we can calculate Bx and By. Then we go to body 1. because dy was calculated from the whole free body diagram. Bx and by came out from the equilibrium equation at the pin. So now body 1 has three unknowns, Cx, Cy, and F. We can write three equations and calculate three of those. So three whole body equations are used. Therefore, three equations for body 2 are automatically satisfied. Again, a pulley cable problem. We are drawing the whole free body diagram, 2 pins, 4 unknowns, 3 equations. Whole body equations are not useful. Now drawing the free body diagram of the components. Force from the top pin, force from the bottom pin. This is the junction. This junction, we added CXCY and CXCY, Newton's action-reaction pair. And the green arrows are the loading that are coming from the suspended weight and the tension in the cable. This is a tricky problem because this free body diagram has 4 unknowns. This free body diagram also has 4 unknowns. So we will have to jump around a little bit here. So first what we do is we balance the moment at A of body 1, and that will give us Cy. We are balancing the moment at A. So Ax and Ay do not contribute to that moment. Cx passes through this point A, so Cx doesn't contribute to that moment. So we can now calculate only Cy. With Cy calculated, this free body diagram has only 1, 2, 3 unknowns. And we can calculate those 3 unknowns. So now Cx is known. In body 1, we have already used the moment balance equation. So now we can still have 2 force balance equations. And the 2 force balance equations will give you Ax and Ay. Thank you for watching.